Hi, welcome back. So, in my last video, we were talking about how we managed to derive the volume flow rate. Okay, being a volume of fluid, right? That comes out from an outlet opening. Okay, and forming a volume of that particular fluid over a certain stretch of a certain amount of time. Okay, and this volume can be seen as this volume of the fluid that comes out, which is typically the cross-sectional area of the opening multiplied by a certain length. Okay, so cross-section area is usually denoted by A, and if the cross-section area is a circular pipe, your area will be pi r squared or pi d squared over 4. Alright, so but now we just keep it simple. Area times length will give you the volume of this cylinder over a certain time. Okay, and I also raised to your awareness that this length over time, if you look at it, is actually the velocity at which this flow is coming out from the opening. Okay, so this is the velocity, L over T is the velocity. So you get cross-sectional area multiplied by velocity. Okay, so Q is equals to U times A. Okay, so if we look at example 1-12. Alright. Okay, before I go there, we also learned that mass flow rate, kilogram per second, is related to Q simply by multiplying Q to the density of the fluid flow. Alright. So here 1-12 we are given the density, the pipe diameter, and the velocity, which means we can make use of this diagram. This is diameter is 32 mm. So in meters it will be 0.032 meters. Okay, and the velocity is 3 meter per second. So U is 3 meter per second. Okay, density is 820. So what is the volume and the mass flow rate? So the volume flow rate is U times A. So U is straightforward 3. A is pi d squared over 4 equals to 3 times pi times 0.032 square over 4. Okay, so this is 8.042 times 10 to the power minus 4 meter cube per second. This is the volume flow rate. No. Times 3. I need to multiply by 3. So this is 2.41 times 10 to the power minus 3. Let's check again. Yes, 2.41 and 10 to the power minus 3 meter cube per second. Right? And the mass flow rate is simply density multiplied by your newfound Q. Okay, 820 times 2.41 times 10 to the power minus 3. Gives you 1.978 kilograms per second. Alright, so these two are the answers. Okay, having been able to calculate both volume and mass flow rate, we now take it as a level higher and put it in some real true meaning. Okay, and we reach section 1.6, continuity equation. Okay, there are a lot of words over here, a lot of descriptions, a lot of guiding principles. I'm just going to put it very straightforward to you. The idea of continuity equation is mass conservation. Okay? Mass cannot be created nor destroyed. Okay, it has to be conserved. If it enters somewhere, it has to leave in another place. Alright, so if we look at a certain system, okay, if there is a mass flow coming in, okay, there has to be some kind of a mass flow coming out, okay, so that your whole mass is conserved. That is the idea of it, okay. And these few pages will talk about this, okay, and it is based on and once you form the equation, it is called the continuity equation. Alright, so I just put it very simply lah. What goes in must come out. Okay, it may sound very interesting and funny, but that's basically the idea behind that. So if you see your page 26, this whole diagram, this mass that go in, right, should be the same as the mass that come out. Okay, if you are to conserve your mass. Okay, if you remember previously when we were talking about the buoyancy force, right? So let's say we have a tension, we have a weight, and a buoyancy force. Then there I was talking about which equation should you start from, okay? And then I mentioned that you should always start from sum of forces equals to 0. This is your starting point. Alright? And then when we were talking about the U-tube manometer, okay, something like this. Then let's say this, okay, forget it. Okay, here, let's say it's here. Okay, 0.1, 0.2. Then I say you start off with the equation of this. The pressure at the same elevation is equal. So we start off as P1 equals to P2. Then we carry on the calculation. Okay, I always have a starting point, and these are useful starting points for the relevant problems. And I'm going to give you the same relevant starting point for such mass conservation questions, and that is the summation of the mass flow rate that is coming in equals to the summation of the mass flow rate that is going out. Okay, mass flow rate. It is not volume flow rate. It is mass. It is always mass that is. It is always mass that is conserved. It is not volume. So your kilogram per second sum up together must be the same. Okay. So once again, let's say I have a system. Okay. Pipe 1 and pipe 2. Pipe 1 and pipe 2 are going in, and pipe 3 and pipe 4 are coming out. Okay, so to put it to this equation, what it means is that m.1 plus m.2, these are the two that going in to the system, must be equals to m.3 plus m.4 that is coming out. Okay, and we know that. Okay, and this is not the end. Okay, you have to expand it further. How to expand? Using the volume, flow rate, and the density. So m dot is rho q, right? So what should be written is the density at 1 times the volume flow rate at 1 plus density at 2, volume flow rate at 2 will be equals to the density at 3, volume flow rate at 3 plus density at 4 times volume flow rate at 4. Okay? So each of them is their own term, and at this juncture, okay, this equation is true, okay, for all fluids. But if then we have to make a distinction between two types of flow. One is a gas flow, the other one is liquid flow. Okay, and what we are saying is this: if your fluid is a flow of gases, okay, the chances are that the density might not be the same as it goes in and as it comes out. So this rho 1, rho 2, rho 3, rho 4 may not be the same. Okay, but if you are looking at liquids, okay, usually our assumption is that liquids are incompressible. Okay, incompressible meaning that the density does not change as it flows from one place to the other. So if this is true, right, it means that my densities are all the same. Rho 1 is rho 3 is rho 2 is rho 4. Okay, they're all the same. So in that case, right, this particular equation gets simplified. Why? Because these are all the same densities and they will get cancelled out. Alright, so what becomes of this equation? It becomes Q1 plus Q2 equals to Q3 plus Q4. Okay, only if the fluid is incompressible. If it is compressible, the densities cannot be cancelled out. Alright, and of course you can further expand this equation because you know volume flow rate is a product of velocity and cross-sectional area. So you will have A1, U1, A2, U2, A3, U3, and A4, U4. Okay? And to make it even, and to break it down even further, if you're talking about circular pipes, all the areas have diameters. So it's pi d1 square over 4 u1, pi d2 square over 4 u2, okay, pi d3 square over 4 u3, and finally pi d4 square over 4 u4. Okay, so this equation is derived based on incompressible and circular pipes, and you can get this, and you can solve the required unknown. So solve for the required unknowns.